Welcome to this lecture. I am Thibault Renaux for the Belgian group Corrugated, and I will present to you design method for corrugated steel sheets. This method is based on test and in consideration of a bibliographic state-of-the-art. All this steps were the subject of the GRISP project in which Corrugated group took part. This lecture is divided in three main parts. First, a contextual reminder concerning cold form steel profile and more precisely the situation of the design of corrugated steel sheet. I will then present you the test campaign carried out during GRISP project, the determination of the characteristic accordingly, as well as the conclusion as to the observed behaviors. Finally, the detail of the calculation method will be exposed with the field of application. Corrugated Group is one of the main European independent manufacturers of cold form steel profiles. The technical assistance it provides to its customers and to engineers is increasingly based on the design method provided by the Eurocode. To do this, it's important to ensure that all products are covered by calculation method in order to give advice on the design. Application of cold form steel profiles are varied. These products can be used for several types of floors. In the case of floors with concrete, the deck can be used as formwork or reinforcement, participating to the resistance thanks to the specific geometry characteristics. We also find the cold form profiles for the realization of dry floors for which the lightness is the main asset. Purlins and spacers are one of the families of products. They are generally used to support simple skin roofing and cladding or for the local support of external skin. We have two different types of application for roofing depending on the slope. Trapezoidal and sinusoidal profiles can be used to realize single or double skin system for pitch roofs. For flat roof, these are usually trapezoidal profiles. For cladding applications, we have liner trays for the inner skin of systems, as well as sinusoidal or trapezoidal profiles for single skin or for the outer skin. Corrugated steel sheets is one of the oldest products in the family of cold form steel profiles. Typically, a corrugated steel sheet is a product presenting a continuous sinusoidal curve. Corrugated steel sheets are daily used for various types of building. Steel envelopes of industrial buildings are made with corrugated steel sheet. Corrugated steel sheet is a success solution for architects. Steel envelopes of residential buildings are made and designed with corrugated steel sheet. Commercial areas like car dealer or establishment open to public, like shop, are examples of buildings made with corrugated steel sheet. Application of corrugated steel sheet continue to diversify, and it's not uncommon to see, for example, sport infrastructure building with corrugated steel sheet. However, this inventory does not reflect the situation regarding the analytical tool within the Eurocode. Indeed, although the corrugated steel sheet have a feedback experience exceeding 150 years in building envelope, the current version of Eurocode don't issue any analytical method to design envelope with corrugated steel sheets. So, the aim of a part of the GRISP project is therefore to propose a design method for corrugated steel sheet knowing eventually bibliographic state-of-the-art. This state-of-the-art reveals that, in addition to the conventional bending theory for which no local buckling is expected for continuous curvature, some information are available in national standard and scientific articles. The German standard DIN 59231 proposed a direct result in function of the depth of profile and the curve radius. In France, In 2012, in the review Revue de construction métallique, an article has proposed a calculation method developed in comparison with a finite element modelization. A specific application of corrugated steel sheet, that is to say for silo application, is covered by a Eurocode, the Eurocode 3-4, in which formula are given. Finally, the older Swedish code for light gauge metal structures give information for analytical design. During the RISP project, the experimental step consists first to perform a campaign of 95 tests in order to validate some information from bibliographic state-of-the-art and to have a complete database to interpret. 2 corrugated steel sheets were selected because they represent the classical products daily used. The first is the smaller corrugated steel sheet with 18 mm of depth, 23 mm of curvature radius, and 76 mm of pitch. The second presents 46 mm of depth, approximately 29 mm of radius, and 150 mm of pitch. They were manufactured by Bacassier in 2 thicknesses, 0.63 and 1 mm. Based on requirements of Eurocode 3-13, a complete test program was performed for the 2 steel sheets. This program is subdivided in 5 types of tests: the single span test, the intermediate support test for both loadings and for different fixing conditions for uplift loading, the end support test, and finally a shear test. For each test, tensile specimens complete the campaign. Applying requirement of Annex A of Eurocode 3-13, the result of each test, in fact the observed resistance, is affected by a coefficient μr depending on the real thickness and the real yield stress of the steel. A statistical setting is performed according requirement defined at paragraph A63 of Eurocode 3-13 in order to determine the characteristic values of each configuration. The first type of test was the single span test. This test consists to applying 4 linear loads simulated a uniformly distributed load as defined in Annex A of Eurocode 3-13. It is used to determine the bending moment capacity on span. This bending moment capacity is determined applying the following equation with FUK the characteristic test load, BV the width of the test specimen, LV the length of test specimen, L the span length, and G the self-weight of the test specimen. At the end of each test, failure mode was noted and occurs by yielding or buckling of the composite part of the geometry. Failure mode occurs by yielding at midspan for small ratio between the radius curvature R and the tilt thickness T. For grit RT ratio, the failure occurs by local buckling, as we can see on this picture. To study the load-bearing behavior at intermediate support, that is to say to determine the design resistance moment on support and the support resistance, 3-point bending tests were carried out according to Eurocode 3-13. This test consists to simulate an intermediate support applying a line load presenting a width corresponding to the width of this support. In such configuration, the test specimen is in opposite position and a device constituted of steel plates simulates the transversal continuity of profiles. In the case of uplift loading, the program was subdivided in 2 aspects. Indeed, 2 fastening modes are possible: fixing in the valley, like in Great Britain, or fixing in the crest, like in France. Consequently, the load isn't applied directly on the steel sheet, but transmitted to the support on which they are fixed. The 2 characteristic values are the intermediate support reaction and the bending moment at support. They are calculated using the presenting equations with FUK, the characteristic test load, BV, the width of the test specimen, LV, the length of the test specimen, L, the span length, and G, the self-weight of the test specimen. At the end of each test, failure mode was noted and was dominated by local deformations and buckling of the compressed part of geometry. In addition, the interpretation of this test consists to draw a diagram interaction between moment and reaction on the support in function of the span length. We can see now different pictures taken at the end of the test presenting failures for downward loading and now for uplift loading. The next type of test is the end support test, used to determine the end support resistance of a steel sheet. It consists to apply a large line load on the steel sheet put in one head on an inclinated support. The length of the cantilevered part of the steel sheet on left end corresponding to the width of the end support to simulate. The characteristic value of the end support resistance is calculated using the presenting equation with FUK, the characteristic test load, BV, the width of the test specimen, A, the distance between load axis and support axis, S, the span length, and we neglected the self-weight of the test specimen. The shear resistance was the object of the last type of test. For this test, the steel sheet is put directly on support according Annex A of Eurocode 3-13. For this test, the line load is applied directly on the product. The characteristic value is calculated using the presenting equation with FUK, the characteristic test load, BV, the width of the test specimen, A, the distance between load axis and support axis, S, the span length, and with neglected the self-weight of the test specimen. Main conclusions of the test campaign are the following. For the isostatic design of a corrugated steel sheet, two methods are possible. The first one is based on the Swedish approach. For the second, it consists to apply some relation given by the Eurocode 3-4. For the behavior on intermediate support, under uplift loading and when the corrugated steel sheet is fixed in valley, the bending resistance moment on support is equal to the bending resistance in span. Outside of this previously case, the results don't show a clear rule allowable to apply, and further studies can be envisaged to determine precisely the influence of geometric parameters. This situation is the same for shear behavior and support resistance behavior. We arrive now to the presentation of the design method of the corrugated steel sheet. To determine the bending moment resistance in span of corrugated steel sheet, we can apply two methods. The detailed method consists in a first step to calculate the RT ratio, the ratio between the curvature radius and the thickness. If this RT ratio is less than 4% of the ratio between Young modulus and yield stress of the steel, then the local buckling of the cross-section doesn't need to be checked. In this case, the characteristic bending moment is simply calculated by the following relation, considering the section modulus of the gross section. If the RT ratio is at minimum equal to 4% of the ratio between Young modulus and yield stress, then for ultimate limit state, the characteristic bending moment can be calculated using the following relation, considering a reduced compressive stress. To determine this reduced stress, it's necessary to calculate first an eta coefficient depending of geometrical aspect of corrugated steel sheet. Secondly, knowing neta, the buckling stress can be estimated and the slenderness ratio alpha in consequence. Finally, the value of the reduced stress is deduced in function of alpha. For service limit state, the inertia can be calculated from the section modulus based on the following relation. The section modulus is then determined considering the characteristic bending moment using a reduced stress corresponding to the yield stress of the steel divided by 1.5. The second method is the simplest. It comes from the Eurocode silo approach and can be applied in a precise field. If the following conditions are respected, steel sheet on two supports under uniformly distributed loads, presenting an RT ratio less than 10% of the ratio between Young modulus and yield stress, with a design steel thickness more than 0.55 mm, and these geometric proportions, then the moment of inertia, the section modulus, and the characteristic bending moment can be estimated with the following relations. When a corrugated steel sheet is an hyperstatic configuration, like on tree supports and fixed in valley, it is possible to determine its bending moment resistance for uplift loading. The value is the same as the value of the bending resistance on span. The other aspects of the design of corrugated steel sheet in hyperstatic configuration must be determined by further studies. I am Thibault Renaux for the Belgian group Corrugated, who participate to the GRISP project. This lecture was on the design method for corrugated sheeting. Thank you and enjoy Eurocode.